or Yale. And, well, what is more related to this talk is that he has co-authored a lot of papers, 12 in particular, with the Nobel Prize Ken Wilson. And they both together founded the method Similarity Renormalization Group, which is somewhat related to what he's going to talk about right now. And, well, with this short introduction, I continue.
Hello. Thank you very much for the invitation. My talk concerns confinement of quarks, which means that they are inside hadrons and cannot be moving separately. Hadrons are particles that are made either from three quarks, like baryons, or mesons, that are made of quark and antiquark. In particle data tables, there are about 200 baryons, and they all are made. And there are about 100 mesons, which are made of quark, antiquark. So this classification in terms of quarks is very powerful. It explains a lot of data, more than Mendeleev table of elements. Quark model explains this plethora of states of matter in terms of just three quarks or a quark-antiquark pair. Proton is one of the most important baryons. The other most important baryon is neutron. But besides proton and neutron, there are so many others who are made of three quarks. So in the quark model, with which the concept of quarks started, mass of the proton is just 3 times mass of a quark. So proton is imagined as just 3 pieces put together. And mesons are assumed to be just quark and antiquark, and their mass is supposed to be twice quark mass. There are departures from these simple rules, but that's the basic idea to begin with. When quarks were invented, the number of known baryons and mesons was much smaller than today. And quarks were considered mathematical tools to explain the systematics of hadrons, baryons and mesons. Not real things. So there was a history of attempts to check if hadrons really are made of 3 pieces in case of baryons and 2 pieces in case of mesons. The one experiment with which I had something to do, no, I'm not saying it right. One experiment which I'm very familiar with was done in Stanford Linear Accelerator Center in beginning of 60s was the project started. I'm sorry, my phone is disturbing me. So in Palo Alto, it's a little bit south of San Francisco, Americans built an accelerator about 4 kilometers long. It contained condensers, about 5 condensers per meter. If it's 4 kilometers long, then you have thousands of them lined up, and when electron goes through a condenser, it's accelerated, and then the condensers are correlated, and it enters the next condenser, and it still accelerates it, and it does it many thousand times. And eventually, the electrons achieve practically speed of light, and their energy, which you probably heard, is given by a factor gamma times the rest energy of an electron, and gamma was tens of millions. Extremely energetic electrons, and these electrons hit a bottle with hydrogen gas, just a little container, which we can imagine as mostly hitting the proton, because electrons are light and they would be shoved away right away. They wouldn't contribute much to light. But protons would be hit by these electrons, which we can imagine in the following way: that electron comes, emits a photon, and this photon hits the proton. It's actually absorbed by the proton, it breaks it into pieces. But nobody knows what happens there. All one observes is this electron. So there is some kind of distribution of electrons flying out at different angles with different energies. And this is what we try to understand. What kind of function of energy these finite electrons have, at what angles, what kind of function is this? And like in the Rutherford experiment, which led to the discovery of nucleus in atoms, the shape of this function is going to tell us more or less what is this electron sending photons to. Spend some time explaining this. So we a priori should have a function of an angle and of the energy of the final electron, which is smaller than the initial electron energy, because it loses energy for destroying proton. So there was a development in theory in parallel considering collisions of protons themselves, not electrons with protons, but proton-proton collisions. And these collisions were described in terms of a model. Nobody knew how proton is made. People imagined, especially Richard Feynman, that proton is made of some kind of parts, and these parts move together. If they move very fast, their motion is very slow from our point of view relative to each other because of time delay, Lorentz effect. And people invented parton model. Parts formed the state. Let's call them partons, because we don't know what they are. So you imagine that if a proton was moving very fast, that it was a collection of particles, these partons, and every parton carried some fraction of the momentum of the proton. So when we describe the collision of the electron with hydrogen, or actually proton, and this proton is destroyed, we could see it this way. Instead of looking in the frame of reference when this bottle of hydrogen stands, we can go to the frame of reference which moves very fast, and then the proton appears like a bunch of free particles that don't interact. An electron sends a photon, and this photon hits a parton and knocks it out. So there is a feature in this event which allows us to think about the dependence on the angle and the energy of this electron. If we imagine that this parton, which had momentum x times p, gained momentum from the photon q, its total momentum, for momentum, was xp plus q. But after it absorbed the photon, it remained itself. I mean, it absorbed the photon and continued. Then the mass of this guy is the same as mass of this guy. This guy carries the addition of q, this guy doesn't, but their masses are equal. And you cancel this on both sides and you're left with this equation. Product of the two and q squared equals 0 because you canceled xp squared. And then you get an answer that if the parton carried x, this x is expressed by q squared and p dot q. But you measure q squared and p dot q. If you observe the final electron, you know how much momentum it transferred to the proton. And you know what is product p and q because you know the proton initial state and you know q, so you can evaluate the product p and q. So there is this variable x, and it has interpretation of momentum carried by the parton that absorbed the photon. This is called the fraction of proton momentum carried by the struck parton here. And the funny thing observed experimentally is that this function is actually a function of x only. Instead of being a function of two variables, it's a function of x only. So you could measure how these partons are distributed in the proton. So you had a picture. There are corrections to this behavior. The dependence on the experimental variables is a little bit more complicated, and it's important, and it was verified, and it's explained by theory today. The fact that this, instead of two, one has one variable here, mostly, is called Bjorken scaling. So what's this function f of x? Well, number one is that x is between 0 and 1, which is obvious. Partons carry it. But then there are puzzles. It's peaked around 1/3. That's already something, because if proton is made of 3, it should peak around 1/3. Well, its magnitude is about 1/3, too. So if you add 3, you get the whole. This function has an interpretation of x, which corresponds to the current carried by partons. Current is charge times velocity. Velocity is related to momentum. So current is carrying is bringing in the factor x. It should be x squared, but there is also coming x in the denominator, and you end up with that. And there is a charge squared there. The charge is squared because you calculate probability, which is modulus of the wave function squared. So even though the amplitude of scattering is proportional to the charge, cross-section or probability is proportional to charge squared. And then there's a probability of some parton having momentum x. And well, you can assume that there are 3 partons, these charges, etc. You explain this figure. Wow, quarks are real. They are not tricky mathematics tools to describe some kind of murky spectrum of some particles that actually are not even stable. But the funny thing is that when you integrate this function f, you don't get 1. That means there's something else carrying momentum, not only quarks. And actually, you get about 1/2. Half of what is in the proton is not quarks. So the discovery was, it's great, but there is something in addition. And what is it? Nobody knew. It's some kind of glue that keeps these quarks together. together. So they are called gluons. So a theory had to be developed about these quarks and gluons. What are they? And of course, we have little imagination. We don't know much. We know electrodynamics. Nothing more, strictly speaking, is really relevant of what we know. So the theory for these quarks and gluons was built in analogy. In electrodynamics, you could have electron-emitting photon. This is how we calculated the cross-section for electron-proton scattering. Charges of the charged particles in QED, you can treat it like numbers. It doesn't matter in what order you multiply them. But when you think about quarks, you have to be more advanced, and quarks have to appear in three kinds. Three kinds because if three of them form a baryon, and it turns out from the measurements of the cross sections that they need to be fermions of spin 1/2, then they should satisfy Pauli principle. There cannot be two in the same state. Because there cannot be three in the same state, how can three form the ground state when there is high symmetry? They cannot be all three very similar in the ground state. So they invented additional quantum number. And they differ by this additional quantum number. And nobody... But it was clear that there must be a quantum number which has three values. And they called it color. We have color. But it only says that these quarks must appear in three varieties. And we call them red, green, blue, but it doesn't make sense. We don't see color of quarks because it's just a name. And this theory differs much from QED in this respect, that when a quark emits a gluon, it does it almost like electron emitting photon, but the gluon is mixing these different kinds of quarks. It acts like a matrix. And matrices cannot be multiplied in any order you wish. The order is important. Gluons are not abelian, we say. And this theory, which is called quantum chromodynamics, in distinction from quantum electrodynamics, is called non-abelian theory. And because there are three quarks colors, it's SU3 instead of U1 in the case of electrodynamics. This information for those who know what I am saying. There is a tricky thing about QCD. Because these gluons are not commuting, and it doesn't matter in which order you multiply things, gluons interact with gluons. So not only quark can emit gluon, but also gluon can split into gluons. And that's why it's a glue, because it's very sticky. And it's producing itself, and it's gluing these quarks heavily. So you can actually try to compute how do they glue themselves. And so one gluon could split into two, but the two could interact again. And actually, there's very many things they can do which combine to the same thing that one changes to two. But there is a factor multiplying the original theory splitting function. And this factor is giving us dependence on how much gluon number 1 moves with respect to gluon number 2. The gluon can split into two, and these two can move with respect to each other as much as they want, from zero relative motion to infinity as far as energy is concerned. And this coefficient is depending on how much the relative motion of these two it has energy. How large is the energy of the relative motion? So you have this function. So the effective vertex, which describes how a gluon splits into two altogether, is not a number, but a function of how much energy the two have. Well, in QED you have a number, e squared over 4 pi hc. You use these. This is alpha QED, fine structure constant of electrodynamics. So here in QCD we have something similar, except that this is a function, perceptible function, instead of just a number. The trick about this function is that when these two move very fast with respect to, or their energy is extremely large, one could say invariant mass of them as two relativistic quanta is very large, and it tends to infinity. This factor, this G12, goes to 0. So we have a funny situation. This glue is gluing quarks very much, but when these gluons move very fast with respect to each other, they practically don't interact. So they look like free particles. Well, that's the Parton model, where we are assuming it's a gas of free particles. This feature that this effective coupling goes to 0 when momenta go to infinity is called asymptotic freedom. Asymptotic in the sense of going to infinity. Of course, we don't go to infinity. Nobody knows what happens at infinity. There is no infinity in our universe view. But large values can be measured, and they were measured very accurately in all kinds of experiments because it's a fascinating feature. Why it is a fascinating feature? Because in QED it's different. When an electron emits a photon, an electron and photon move a lot with respect to each other, an analogous function, which we don't see at our home energies, analogous function blows up to infinity. And the theory breaks down. It just doesn't work at all because the interaction is so strong that we have no idea what happens, and quantum electrodynamics is kind of sick theory at very large energies. And that means that we don't have ideas about how to do a theory which could be true to the very end, to the largest energies, shortest distances. This is a mystery. But if this coupling goes to 0, then perturbation theory is more and more accurate. Everything we calculate into a series of powers of the coupling constant, this effective one, and the larger the energy, the closer these gluons come together and quarks come together, the more accurately we can describe it with our poor mathematics of few terms. So we suddenly are as wise as God who created the universe, because we know exactly what happens at infinite energies or infinitely short distances, and we know as much as you can do. So that was fascinating. So people were measuring. So this is a quote. This figure is taken from this website. You know, I'm doing it legally, I hope, reproducing it here. I assume that I'm not violating any law because I proceeded according to the instruction on the website. So this Q, which is on the horizontal axis, this is 10, this is 100, this is 1,000, is in GeV. So 1,000 means the mass of these two particles is 1,000 times bigger than proton rest energy. 1,000 times bigger. Heaviest nuclei are about 200 nucleons. So you have 5 nuclei rest energy gold. 5 golds at the rest energy of 1,000 here. So this Q corresponds to this M, and the asymptotic freedom means that when Q goes to infinity or M goes to infinity, this coupling falls off to 0. And this is experiment. So we have to accept it. And the other side of the coin is that when the energy of these two that come from one goes down, this is 10 proton masses, this is 1 proton mass, this coupling grows. And this is called infrared slavery, because the interaction is so strong. When they don't move much, they interact very, very strongly. They interact so strongly that all mathematical methods we have are no longer applicable. We cannot expand it in a power series. This coupling is exceeding 1. You cannot expand in a series of powers. And so people have to engage computers in the computations, and they let the computer, contain everything we know, and it crunches huge numbers, really giant memories, thousands processors, and it produces a number eventually. But we don't understand what happens in the meantime. We don't understand what artificial intelligence is doing when it's giving us a number. So in QED, we have a completely different situation than in QCD. In QED, the coupling really matters. This E squared over 4 pi is 1/3. In QCD, you saw on this figure, when we come down to about proton mass, we have alpha order 1/3. That means G is 2. No hope expanding in powers of G. Every new term will be much bigger than the previous term. We have 2 charges. Photons practically don't interact with photons. They are abelian. They don't scratch each other in any way that would be relevant. And you have a dipole field around a pair of electron and positron. In QCD, gluons interact with each other. They actually want to grab themselves. And if they have low energy, low motion relative to each other, they grab themselves stronger and stronger. So when you spread antiquark and quark, and they emit gluons, these gluons catch up on other gluons, and when you pull them, you produce such a string. The gluons don't spread like photons do. Photons spread around and they form dipole field, electric field. Gluons don't spread. They hold together and they form kind of sausage between quark and antiquark. That's the result of these huge computer simulations. And when you have this string, you get about 1 proton mass per Fermi. Proton size is about Fermi. If you pull quarks by 1 Fermi, the string in between costs about a proton mass as far as energy is concerned. You pull 10 Fermis, you have inputted into the string 10 proton rest energy. So the meson now would be a quark and an antiquark and a string of gluons in between if you try to pull away. Baryon, well, that's a question how they are built. Actually, there is no conclusive answer how a baryon looks like. For a century, almost. And, uh, and when you have this string, you get about 1 proton mass per Fermi. If you pull quarks by 1 Fermi, the string in between costs about a proton mass as far as energy is concerned. You pull 10 Fermis, you have inputted into the string 10 proton rest energy. So and we don't know how they are built. And this configuration is equally possible today as this one. And this one is called quark-diquark, because quarks are considered to be close to each other and separately positioned to the third one. And it's so difficult to understand because this coupling is so strong. So these particles live their own life, and we don't know what that life is like. So the question is, can one isolate a single quark? And the answer is no. Not yet. I mean, maybe someday, maybe you will invent some method and shoot something into the proton and the quark will come out. So far, it was impossible. QCD is a theory which says that when you have a quark and antiquark connected by a string, and you never have any other configuration, there's always a string between colors to form a white object. When you pull such strings, at some point the energy of the string is so large that the theory will prefer to create extra quark-antiquark pair. The string will break, and instead of having free quark, you will have another meson again. And you never see quarks. Only mesons and baryons, no matter what you do. And that's the confinement today. Quarks are bound by gluon strings. And I describe to you what is written in this sentence. It is written that pulling quarks creates extra q-bar pair because string is so energetic, and you never see a single quark because it's better to see a meson according to the theory. But, okay, but why can't we really knock a quark out? I mean, separate it so sharp. If I had a big knife sharp, I could just cut it off and let it go. What would happen? And this is what I want to tell you about why I am here. I'm here because Maria Gomez Rocha invited me, and she works on Hamiltonian formulation of quantum chromodynamics. And there are two other people, Kamil Seraf and Jai Moore, who was heavily involved in work on a new take on the issue. And we're trying to develop quantum mechanics of this QCD stuff that goes on when this coupling constant appears to be so large. Because this coupling is so large and it depends on the mass of produced particles, it's very hard to figure out how to write the Hamiltonian for them. It's not a simple thing because of this scale dependence on energies. But the dream is that you can develop such a Hamiltonian and then write down the Schrödinger equation, and baryons and mesons would be eigenstates of this Hamiltonian. This would be physical objects that evolve only with phase and may be stable. They may actually also decay when they are excited, okay? Like atoms, excited atoms decay to ground states. But it would be quantum mechanics per se, instead of some kind of Parton model with theoretical additions. And then the evolution of states would be described by the exponential of this Hamiltonian, which, if we knew eigenstates, could be somehow described well in terms of these eigenstates. And the question is, could a single quark move around according to this Hamiltonian? And the trick we are using in the calculation, therefore we are different than everybody else, is that we do something about gluons, which is very fundamental. Gluons are interaction carriers of so-called gauge theory. In essence, photons are massless. QED is a gauge theory. This goes together. When you try to mimic QED, when you build QCD, you want to keep gluons also as massless, to keep the symmetry similar to the symmetry of QED. But we propose put some non-zero mass there into the Hamiltonian that screws up the symmetry. But we put this mass very small. And because it's very small, you can go to the limit of this mass going to zero, and you should recover something, some information about the theory that has mass equal zero. And it's actually happening. But it turns out that this limit of this mass going to zero is not trivial. It remembers the variation of the coupling. It remembers how these states must look like. And when we do this Hamiltonian trick, and we change a theory with this mass equals zero to this theory with mass a little bit not zero, and experimentally you don't know that it's zero. Photons are considered massless, but experiments tell us that they are only 10 to minus 28 times electron mass or smaller. We don't know that photons are exactly massless. We know that their masses are extremely small. The same with gluons. The limit on gluon mass is bigger than the electron mass. The gluons could have 1 MeV, which is twice electron mass, and nothing would change in the explanation of experiment by theory. So we make this assumption, and then we pose the eigenvalue problem for this Hamiltonian, which is different from QCD because it has non-zero little parameters stuck there. We do it in perturbation theory, which we know how to design. We know how to write this equation, and we obtain these eigenvalues approximately. Now these eigenvalues, remember that there was some scale involved. In the Schrödinger equation, we were not asking about any eigenstate. We were asking about eigenstates that have masses of about m. And there was this little parameter, and we go to zero, and we use very low order perturbation theory because we can't do everything at the same time. It takes time, it's difficult, it's not trivial, it's very tricky, it's fascinating, it's intriguing. Maybe we're understanding something, and we want to understand more, and here's what happens. If we consider QQ bar and the zero, I mean, the colors are such arranged that we don't see any color, then the eigenvalue in that limit stays reasonably close to what it should be, according to experiment. But when the mass of the gluon goes to zero and we consider a state which has color, so colors are not combining like vectors into a scalar, but into some kind of tensor, like tensor product or vector product, you call it. How do you call it in Spanish? There's a scalar product and... Okay, you know what it is. I mean, I didn't hear well. So when it's actually having a color, such a QQ bar pair, then when this mass goes to zero, our solution goes to infinity. You can't have a finite mass QQ bar which is not color singlet. It cannot move around. And if you have a quark, you can pose the eigenvalue problem with quark quantum numbers, and tend with this mass of the gluon to zero, you get infinity. There are no quarks to fly about because they immediately dress up with this glue, and this glue explodes like you throw lithium into water, and it immediately cooks up and has infinite energy. To give you just a brief look at what happens is that quarks interact with themselves. They can emit gluons and absorb gluons. So they have self-interaction. And they can exchange gluons. And it happens that the self-interaction is blowing up to infinity like the scale over mass of the gluon, which we send to zero. This one for antiquark is doing the same, but the exchange provides -2 times the same logarithm. And you end up with a finite, and actually reasonable finite answer what's happening with the quarks. But if the meson is colored, you have these self-interactions, and the sign of this exchange changes because it's this non-abelian theory, and the order of multiplying matrices matters, and if you change the color of the whole system, you switch the sign, and 4 logarithms add up, and you get 4 times infinity instead of cancellation. And similar thing happens in single quark case. So my conclusion is that our Hamiltonian formulation of QCD complements these established approaches and provides new options for research on how confinement works in a truly quantum theory. That's it. Thank you. In distinction from the string picture, when the claim that quarks are confined because they are always forming the string, and the string to break is the only way of avoiding huge energy when you pull them apart, this statement is replaced by the statement that there are no finite energy single quark states. So you can't produce them, because you would have to provide infinite energy to them.
And then you have nicely introduced what gluons mean and all these beautiful words that they with the history. Does a string theory is born at the same time when you were explaining about the string?
Oh,
string theory was born in such a way, or?
Yeah, initially.
Yeah, initially.
Strings were. I don't know. You know, we've been playing with strings of all kinds. Okay, you take a stone and. But initially, strings were considered for QD because people wanted to understand how they bind. And string theory of gluons turned out so difficult, as it is, yes, that there's little progress about those strings. It's actually interesting why the progress is slow. One of the reasons, I think, is that it's too difficult for most physicists, and so they give up and don't do this anymore because they cannot get a position. They cannot money. They cannot get money for doing this because they can do this for a long time and nothing comes out. So string theory of basic properties of the universe is a different story. It's not about these strings. These strings are too difficult for string theories of this fundamental stuff, because they can speculate there so much that whatever they do, they can publish and claim it's worth money. they can't do gluon strings because they are too real and too difficult. Okay, so there's this string theory which is developing mathematically. Wonderful mathematics, really great advances in math, but not much conclusions about physics of fundamental questions like what is electron and what's inside a black hole, etc. So, I mean in the center black hole. So, what I should say is I'm not an expert on string theories, and it shows. And it shows. As far as QCD strings are concerned, it's a difficult physical problem.
More questions?
Is the gluon mass you use as an infrared regulator? Is that the use of the why do you need to give mass to the gluon?
If I don't, then they are massless, and arbitrarily large numbers of gluons may have arbitrarily small energy. So they can form a glue in so tricky ways that there's no way to understand it in simple terms. Like turbulence. I mean, the river flows and all these swirls, you know, all depths, all size, from swirls of the size of molecules of water to the swirls that, you know, can grab part of the shore and wash down trees. So it's very complicated. When you give it a mass, suddenly you throw away almost all of it, and you can slowly inspect what happens when you make this mass smaller and smaller and smaller, and you get control on these logarithms. And you see early enough what may be happening when you go with the mass to zero, while you don't have to know what happens at exactly zero.
It's like a kind of infrared cutoff.
Yeah, it's playing the role of very special kind of regulating infrared singularities so that you can manage computation in hand in lowest order and understand what may be going on. And that's what I was trying to show.
I mean, as a question, as a fully outsider, can there is any experiment that can tell you the limit of the mass that you are including? The gluon mass that cannot be measured?
Gluon mass experiment is experimentally limited by a few MeV, which is like a couple of electrons or even more. So experimentally you cannot distinguish massless gluons from massive gluons. The theory assumes they are massless. No way they have mass. And this big problem with all of them producing arbitrary numbers. If you insert the mass, you bring some kind of order to your thinking and you begin computing.
Wilson also invented the lattice gauge theory.
Yes.
What do you think about lattice gauge theory approach to solving the problem?
I spent a long time with Ken talking about QCD. And he taught me a lot. I mean, I owe him my not dropping out of physics. I was ready to drop physics of these difficult questions because people were doing something about it, but it didn't make sense to me to the extent that I would like to engage my life in it. And I was ready to move out, and I met Ken, and he explained to me enough that I began to be interested again, because there was some kind of thought behind the theory. It wasn't just guessing. And Ken was very interested in understanding how to do better than lattice. Lattice is a wonderful tool It provides you answers to definite questions, but it does not explain to you what's really going on in detail. It's providing you a final answer. Therefore, I made this comparison with artificial intelligence, that you ask the question and here's your answer. And what was happening in between? People already don't know. And there's a danger that computers will begin to govern us, and then they will decide to kill us because we don't know, take too much sunlight for our batteries, or I don't know. There's certainly all kinds of dangers in the fact that we don't know what artificial intelligence is doing there on its own with these billions of bits or maybe even qubits. So lattice theory is formulated in a certain special way to answer certain questions. When you begin to ask what happens when you change the frame of reference, in other words, you start moving with respect to the lattice, it's kind of difficult. Lattice is formulated in the Euclidean fashion, where time is considered imaginary. That helps in some situations, but it doesn't help in situations when you have a lot of particles and you need to consider chemical potential, which brings in back complex numbers to lattice calculation. And there are various questions about physics of hadrons, in particular protons, neutrons, and the mesons that are responsible for nuclear forces at large distances. The forces between protons and neutrons in nuclei that keep together nuclei, despite that protons are charged and try to fly away. Strong interaction is stronger and keeps the charges together. So it's very basic to our existence that nuclei can exist. And so one is facing a lot of questions that lattice is not prepared to answer for us soon. And the outlook is that even if it eventually provides some parameters that characterize this, what happens, we will still not know what the computer is actually doing. I mean, we will not be able to trace all the up and downs of the bits that are really transformed according to the theory. We will only know the answer. We already know the answer. There are nuclei. So if you want to understand more, people should look for various alternative ways, and Ken was very much interested in alternative ways. And I can single out one basic reason for that interest, which is pretty universal and should be appreciated much more than it is, namely quantum field theory like QCD should have a ground state, which we call vacuum. And nobody knows what it is. All protons, mesons, protons, neutrons are excitations of that vacuum. If this ground state is in its lowest energy configuration, and you excite it, form some kind of bubble in it of excitement, that's supposed to be hadrons. Like you create proton and antiproton. But we don't know what the vacuum is, and it's a horrible problem. People try to understand how to describe vacuum with quantum field theory, and they made errors by 10 to the power 120. Okay, it's a nonsensical situation. We don't know what the vacuum is. If you do calculation with this Hamiltonian approach I was alluding to here, the vacuum problem is completely transformed, it's different, and we can handle the situation without knowing what the vacuum is according to these other formulations where they don't know what it is. Vacuum, empty space is the biggest question of theory that people have no idea about what it is.
Bye.